ladies and gents. Welcome to your guided tour, your walkthrough of our lab. It's called the Radioactive Decay Lab, and it may have been nicknamed the M&Ms Lab, but there is no requirement for you to actually use M&Ms. May I suggest that as you're building this lab, setting up to do this thing and answer the questions on it, it really doesn't have to be M&Ms. I'm going to use, as my example here today, I'm going to use pennies as an alternative. Really, it can be anything that has one side that has a difference from the other. So take a look at the M&Ms. Some of them you can see the M side up, and then others land with the M side down. With pennies, heads, tails, it works just as well. So let's walk through this. You've got your lab printed out, or you can write it on your own piece of paper if you don't have the printing capability. You have something you can count, somewhere where you collect your sample and don't disturb it once you pour it out, and of course something to write with. So we're going to go through this exercise together, part by part, starting with the beginning. So take a look at section 1. All the supporting data. Most of this is straight copied off of 2.1 and 2.2 that you filled out those worksheets already. Lots of good information on those that you can use to fill in these answers. So, how old is the solar system? We know, 4.6 billion years. How old do we know this? We can measure the age of the rocks. 3 samples. Where are they from? We know moon rocks, asteroids and meteorites that crash down on the planet. We can measure those. Or the oldest rocks that were part of the Earth originally. So old Earth rocks. What is radiometric dating? It is our ability to measure the age of a rock, a sample, by looking at its radioactive decay. The title of this lab, Radioactive Decay. What is an isotope? Isotopes are different versions of the same element, the same atom. Examples being carbon-12 and carbon-14. Carbon's normal configuration is 6 protons, 6 neutrons, 6 electrons, and the isotope has a couple of extra neutrons. That's the one you drew in your drawing on worksheet number 2.1. What's it called prior to radioactive decay? Well, before an isotope changes and loses its extra neutrons, it's called the parent isotope. After it decays, it loses those neutrons, and it's called the daughter isotope. Half-life is the measurement of time it takes to go for half of your sample to go from parent to daughter. So all of these answers you have in your prior assignments, and you can easily look these things up on the internet. Make sure you have everything filled out, and then you have a good understanding of these terms before you move on. All right, let's take a look at our next part, lab setup and materials. This part down here, what materials are we using? I've got something to write with. I have something to calculate with. I think I'll have my cell phone handy and use the calculator on there. So that'll come in handy in a moment. Use a regular calculator if you have those. They're easier, I think, than a cell phone. So I've got my sample, my calculator, my tray, and something to take notes with. Okay. So you can fill in those 4 blanks. There's your things. Okay. And please note, it says on the slide in front of you and on your paper, the half-life of M&Ms is, in our example, I've chosen 2 billion years. Now, M&Ms, pennies, just use 2 billion years and you'll be okay. There's your time measurement for a half-life. Hypothesis. One of the most important parts of this lab is developing a good, solid, testable, educated guess. You're going to put down a prediction, um, and then you're on the back of this paper. You can actually do the work and see what results you get. So here's your educated guess. Check it out. On the slide in front of you, the video here, it says if and then. You have to make sure your hypothesis is a full sentence and that it has the words if and then. Okay, so let's consider, as we're writing this, what are we going to do? We're going to do some counting and some calculating. Okay, we're going to count sample. We're going to calculate the numbers we get. So if we calculate and count correctly, then we're going to find out right there. That's what we're after, my friends. Okay, the age of our sample. So your hypothesis, make it a solid, connection of what you're doing with what you hope to find out about your sample. That's the point of a hypothesis. Okay. All right, let's move to the back now and do the actual counting and calculating. Here we go. I'm going to use pennies in one tray, and I'm going to use M&Ms in the other. I'm going to do them both so you can see how either one, both of them work just fine. Okay, so let's take a look at our procedure. Up here on your paper, number 4, it says pour out your material sample onto a small plate. Don't touch or move the sample around at all once it's settled. The ones with the M side up. So here we have an example. The M on the green M&M is up. The red one shows blank. The M is gone. Okay? So in this case, the M is our parent isotope and our green is the daughter. It's already decayed. We're not concerned about that one as much. This is the one we'll be counting and comparing it with the total of our sample. For pennies, my friends, let's take a look. I've got a heads side up. We'll go with that one as the parent, and the tails side will be the daughter. Again, we're not going to count the daughter except to double check our math. What we'll be calculating is the heads compared with the total amount of the sample. Okay, so I am ready to do this. I'm going to start with the pennies. Okay, however many pennies you choose, make sure it's more than 10 or so, and I'm going to splash them onto that plate. Make sure that I can see them all, so I will not turn them over. I'm going to spread them out, and once I spread them out, I cannot mess with them anymore. All right, so now I can see them all. That looks like a good sample to me. All right, now, if you choose to use M&Ms, I'm going to take a big old handful like that and spill them onto the plate. I need a little more. Let's see. All right. Looks like they are all sitting and I can see them all. So I have my 2 samples. All right. So let us begin the counting. All right. Count the total number of your sample. I'm going to count this total and I'm going to count that total. And whichever one you choose, I'll do, in my example, pennies here. So if you're using pennies, there's your example. If you're doing M&Ms, I'll do my M&Ms here. You do not have to do 2 of these. Please just only do 1. That's totally good enough. Okay, so I will start with the pennies. It says count the total number of, in this case, pennies. All right, so I'm just going to count to myself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. I lucked out. Oh, and there's one hiding. I'm going to make that 31. Now, I will double check that in a moment when I compare the parent isotope and the daughter isotope and make sure they match up. Okay, so total with M side up, in this case heads. I'm going to count just heads. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I counted 14. Now I'm going to double check that in just a minute. So far, I have 31 total with 14 that are heads, basically. All right, now I got to do the total number for tails just to check my math. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did I miss one? I might have missed one because look at my math. 14 and 16 do not add up to 31. They add up to 30. So I must have missed one. I'm going to double check my counting really quick. This is important that you do your counting and double check it. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whoa, how did I get such a difference with heads? Let me do this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, now my M side up is getting 16. Okay, and my tails should be 15 this time. I really miscounted. All right, here we go with the tails. I'll start on the other side this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, that time the math adds up. So now I have good totals. 31 total, 16 heads, 15 tails. 16 are not changed. I call that parent. And then the other one is daughter. Okay. Now we're going to do a little calculating. My parent number is going to go here. My total number is going to go here. Please don't write the arrows on here. I'm just showing you so you can see where it is. All right, so 16 divided by my total original, 31. Okay, time for calculator. Let's see what we got here. 16 divided by 31 equals. All right, so I'm going to write this nearby to my percent, 0.516. So I've got 0.516, and I have to turn that into a percent. And if you remember, the way to turn a decimal into a percent is you move that decimal point over 1, 2 spaces. So 0.516 becomes 51.6. So my percent sample that is still parent out of the total, 51.6%. Okay, so I've got a good number to start with. That's a number I can work with. Now, to figure out the number of half-lives that have gone by, I'm going to make this number match one of my known amounts. So which one is it closest to? 51.6. Which one does it round nearest to out of my totals? I think 50% is the closest to 51.6. So I'm going to write that in the blank. I've rounded it now to 50%. All right, now I'm going to take this 50% and go over here and figure out the number of half-lives that match 50%. Well, one half-life, one half of it's gone, one half-life. And I'm going to put that over here, 1. Okay, so whatever your total is, whatever your percent is closest to, check the number of half-lives and write it over here. Could be 1, could be 2, could be 3. I had one student last week who actually had 4 half-lives because his sample still with heads up or the M side up was so low, 4 half-lives had gone by. But whatever your number is, make sure it matches your data. Then, I'm going to multiply this times the half-life of M&Ms or pennies. What did we decide that was? I'm going to go back to the front side. Okay. And it says down here, half-life of M&Ms. Here we go. 2 billion years. Cool. So here I'm going to put 2. All right. And now I have an easy math problem on my hands. 1 times 2 billion years, and I get the age of my sample of pennies. 1 times 2. 2 billion years old. And we're done with our calculations. Now, quick check. Did I do the math right? I double-checked my counting and caught my mistakes. So yes, I believe I did it right. My calculator calculated that correctly. I rounded it correctly. I got the correct number of half-lives, and I multiplied it by a known quantity. So my science is solid. Okay? All right. I'm going to set this aside just for a second for those who are using M&Ms. If you happen to be using M&Ms or Skittles or any other kind of candy that has a little mark on it, right? You can use Skittles. It's perfectly good. All right, let's do the pennies really quick. Or M&Ms. Count the total number of M&Ms. Oh, I've got a lot on this plate. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And again, I'll know in a moment if I counted my 36 M&Ms correctly. All right, M side up. Let's take a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm going to double check because I'm not confident I did that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, that time I counted 17. So with 17 gone from 36, I should end up with, let's see, 19. No, that's wrong. We'll see what I end up with blank side. Maybe it is 19 with the blank side up. Let's double check. Ooh, there's a yellow one there that has the M up. I'm going to have to account for that one. That's hard to see. So sometimes science can be really meticulous. You got to be very careful with your counting. Okay, let's count the blank ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I believe I forgot to count that before because 17 and 18 make 35. I'm off by 1. Time to recount my M side up, my parent isotope. And I'll begin with the one I believe I missed last time, the yellow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. One more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There it is. That time I found my mistake. An even 18 and 18. Okay, 18 plus 18 equals 36. My math adds up properly. The ones with the M side up are my parent. The ones with the blank side up are my daughter. All right, so our data collection is looking good so far. Now we calculate. Come on back, calculator. Okay, now the math is going to be really easy. I have an even balance, 18 and 18. Clearly, this is exactly half. We're going to do the math anyway. My total number will go here. My parent goes here. My total number goes there. So 18 divided by 36. And I get 0.5. So I'm going to write 0.5. And you can always add a 0 after the decimal and it doesn't change the amount. So I came up with 0.5 as my division problem. And if we move the decimal over 2 places, we end up with exactly 50%. It is a match. It is a perfect match for one of my percents that I'm rounding it to. So that one goes straight to 50%, and I just write it again. All right. So on my chart, 50% means one half-life has gone by. I'm going to circle that. One half-life carries over. Okay. And multiply times our known quantity, half-life of M&Ms, 2 billion years. So 2 billion years, 1 times 2 remains 2 billion. Okay. 2 billion years. There we go. Now we finally have got to our answer that we were seeking. 2 billion years. All right. So take a look at this. This is interesting. We did pennies in the one example. We did M&Ms in the other. Both of them turned out to be 2 billion years old. Your answers might be similar. Your answer might be very different. Go with what your data shows you is right for your sample. All right. So we're done with our calculations. What is our final part? It's our conclusion and reflecting on what we did. Did we do it right? Did we follow the scientific method? Did we skip anything? Did we leave anything blank when you filled out the front? Is something incomplete? Is your hypothesis something that your experiment actually tests? Did you write a good educated guess? So this is where you look and see, did I do science correctly? Did I miss anything? Did I skip any steps? Are my calculations mistaken? Are my numbers, do they make sense? If you end up with a number 20 billion, that's older than the universe. That's not possible. So this one, you would question if it's a huge number beyond the age of the universe, as an example. So give it one last check. Answer your conclusion. Answer your reflection on the scientific method. And think to yourself the final step. The final step in the scientific method is to publish your results. If we were making a cure for cancer and we came down and we found the formula for something that cures cancer, we would publish it in an academic journal. We would get it out to the public that way. In this case, it's a high school science lab, so it's not going to be published in a magazine, but you still have to do something with your work. Student, your teacher has asked you, what do you do with all assignments when you are finished? What do you do? Write that down as number 8. That is your publish step. Okay? If you have questions, reach out to me through Canvas. Make sure nothing is blank, front and back. Turn in your results and get your grade that you're proud of. Okay? Speaking of proud, I'm proud of all of you for what you're doing in the midst of all this craziness. Keep it up. You guys rock.